Air parcels. The concept of an air parcel is used throughout atmospheric thermodynamics and atmospheric dynamics, so it's an important concept to get our heads around. It is, of course, a theoretical construct, but it's a useful one. Firstly, an air parcel must have a small size, small enough such that temperature, pressure and velocity are the same everywhere in the parcel. In other words, there's equilibrium within the parcel. But it also needs to be large enough for the temperature and the pressure to be defined in a statistically meaningful way. In other words, our parcel needs to be big enough to be considered an ideal gas. An air parcel needs to be thermally insulated from the environment. No molecular conduction or turbulent mixing at the parcel boundary. No net radiational input. And so there's a thermal contrast all along the boundary between what's inside and what's outside. Now that's best defined by having the idea that there's a boundary that's about 10 mean free paths. A mean free path in the atmosphere is about 0.1 microns. What's a mean free path? Well, think about running through a large crowd where there's a small distance between people. The closer the distance between the people, the smaller the mean free path. In other words, the smaller the distance that you travel before you run into somebody else. But if you run in an empty field, then clearly the mean free path is very, very large. So what this is saying is that the boundary between the parcel and the environment is sufficiently large so that the turbulent motions mean that there's a largely a separate population of gas molecules inside and outside the parcel. Now, over a large period of time, of course, there's going to be a large turnover of those, but over a short period of time, we can consider the populations to be essentially distinct. The parcel must initially be in thermal equilibrium with the environment, and it's going to change the temperature depending on what we do to the parcel. The parcel environment is assumed to be in hydrostatic equilibrium. So if the parcel rises, there is no compensating down motion in the environment. The parcel doesn't mix with its environment. That's not always assumed, but it will be for the moment. And the parcel is always at the same pressure as its environment. We ignore frictional forces between the parcel and the environment. So if it's going to rise, then there's nothing slowing it down. And the parcel's kinetic energy is a negligible fraction of the total parcel energy. So things like the heat that it contains and the height at which it's at, that is the potential energy, are more significant. We also assume that any liquid water that results from condensation immediately rains out of the parcel, so the parcel's not weighed down by the liquid water. Or another way of saying it is that there's no water loading of the parcel. There are some problems, of course, with parcel theory. It's difficult to know exactly how big a parcel really is. There's also the issue of when we lift or cause a parcel to descend, why we're doing it to a parcel and not an entire layer of atmosphere. Parcel theory also fails to address entrainment of the environmental air, that is, mixing between the parcel and the environment. Drag, which is the frictional interaction between the parcel and its environment. Compensating motion by the environment, and the condensation of water effects. So atmospheric convection, that is the results of buoyancy of parcels of air being warmer or cooler than the environment, is more complex than this first approximation. But what the parcel theory does allow us to do is to assess things like stability quite well.